Hi, my name is Duane Knudson, and I'd like to thank the ASBeast conference organizers for this invitation to be chatting with you today. So, who am I? I earned my PhD in biomechanics from the University of Wisconsin-Madison, so my training in research is in sports and exercise biomechanics, and much of that work has been in tennis and exercise movements and equipment. But I speak with you today about my recent work in biomechanics research quality issues. I tell my students the best movie of all time, in my opinion, is The Matrix. But I am not the one, and I am here to free their mind. Greetings also from the American Society of Biomechanics and the International Society of Biomechanics in Sports. Biomechanics research has much to contribute to the theory of human motion and application in a variety of areas. Unfortunately, these contributions may be less than ideal for several reasons. I will highlight a few of these in this presentation. This is not a Debbie Downer talk, but an opportunity for biomechanics community to dialogue together about these issues, and I hope to see you in our live panel discussion. Science advances from high-quality research, so peer review and our reading of research should always focus on quality, not on publication outlets or the impact factors of journals. Don't judge books by their cover. Publication in prestigious or luxury or high impact factor journals are good, but that does not guarantee quality or impact. Article level and author level citation metrics can be used with caution as confirmatory evidence of usage in the scientific community. Again, not impact or actual contribution. This was amusingly expressed in a recent research article titled on citation metrics, poking fun at Web of Science hot articles, or Nobel laureates are not hot. I urge you to sign the Declaration on Research Assessment, pledging not to misuse citation metrics like the impact factor, and judging research on its merits. So I was interested on those merits, and I sought data on the quality of original research reports in biomechanics, focusing on factors that minimize potential bias or error. First study specifically in the International Society of Biomechanics in Sports Proceedings, in the Journal of Applied Biomechanics. This baseline data indicated large percentages of original research reports in our field with errors in statistical analysis and reporting, and essentially equivalence between these two applied publication outlets. Most papers inflated the type 1 error rate through testing of multiple, often correlated dependent variables, did not report vast majority of the assumptions of the statistical tests, and would mix tested and statistically untested observations in describing and interpreting the data. And this was similar to common design and statistical errors prevalent in high prestige medical journals. And we'll return to this problem later in the presentation. Fast forward a decade to the second study, and there's not much evidence of improvement in the design statistics complexity score that I applied to articles published in the Journal of Applied Biomechanics and in Sports Biomechanics. So despite large increases in collaboration and numbers of co-authors working on studies, there was not an equivalent, actually only a minor to virtually no change in the level of quality of the research designs used in our field. So one of our most recent studies again reported the same sort of trend of no improvement or no major improvement in sampling despite over doubling of the number of co-authors working on studies. But there was advancement in data collection, modeling, and analysis over the past 30 years that provide some positive limitations or some positive trends for us. Notice that there is a gradual limited improvement in randomization, assignment of participants into random conditions. But again, that's a very, small increase in trend, and again, improving from substantially zero randomization over 30 years is pretty easy. And there wasn't much change in sample size, and we'll return to that sample size again. So the only conclusion from all these studies in biomechanics is that there really is an orgy of promiscuous co-authors and orgy of multiple statistical tests of correlated dependent variables that inflate the type 1 error rate, and make it difficult to believe the results of some of the studies in our field. Fortunately, not all the quality indicators in this 30-year study of the Journal of Applied Biomechanics were bad. There were some small positive trends, again over 30 years, of a very small reduction in the number of dependent variables tested in the studies, and again a very small but in a positive direction increase in the number of trials that were collected with it for each participant or sample to be analyzed, so we could take into account variability. So we don't live in scientific Camelot. Let's look at some other common errors of biomechanics research and acknowledge these blind spots so perhaps we can work together on improving it. So high quality research has to start with asking good and the right research question. And this requires a critical review and synthesis of the results of the previous studies in the field on the topic, all correctly cited and referenced. However, that's a problem because much of our previous research may be incorrect or biased because of those errors I was talking about. And we will explore most of these examples later throughout this presentation and perhaps in the panel about research design, statistical errors, questionable research practices that are very common in biomedical research and in biomechanics. Again, this is important because research is expensive, and when we make errors in our research, our field is generally, and science is generally slow in making self-corrections of these mistakes. So we have much to improve on. Remember that, again, we are not alone on this road to improvement in research quality. There is widely reported research reproducibility problems in most areas of science, and even in the most well-funded medical research field and the most rigorous level of designs, randomized control trials. Most of the studies, 60% of the studies, are inadequately reported, and it is only slowly getting better over the past 15 years. So even when you have large funding and time to do the best quality research, a lot of times all the best practices aren't followed to make sure that we get the most robust results possible and accurately reported. So first, the accuracy of our synthesis of previous research is generally poor. And when we have journal word limits plus the number of citations you're allowed to have added to maybe vague, sloppy, or in a hurry sort of research report preparation, empty references, and citation errors, we end up with poor synthesis or understanding of the context of research to design good questions. So strong synthesis of results or weighing of the quality of evidence is not common at all in biomechanics, despite numerous levels of evidence systems in which to evaluate the quality of evidence for certain inferences. And so I grew frustrated with vague and unfounded speculation in the results and discussion sections, where a descriptive study might say the research suggests something at all in application, when the rules of evidence and inductive logic do not allow us to make generalizations or inferences from descriptive data to something prospectively happening mechanistically. So this frustration led to 2 articles on improving this critical review and synthesis of research, or evaluating the levels of evidence for various inferences. First article is specifically in kinesiology reports and pointing out these problems, and the second one was in our area here on citing levels of evidence for application in the journal Sports Biomechanics, who has an explicit mission to do applied exercise and sport biomechanics research and then provide evidence of application. And both of these systems use similar adjectives about the strength of evidence and the types of research you would need to have to make those qualitative judgments about results. So I urge you to consider that. Now, these errors in critical review align and are related to the second kinds of errors that reduce the quality of our research. First is poor study design, and then we'll talk about the kinds of sampling we do in our studies. Now let's begin with the long-running debate in biomechanics research design, best popularized by Barry Bass, who argued for within-subjects designs rather than the traditional between-subjects designs in biomechanics. Because not everyone is the same, And I'm sure you've all heard of the tyranny of the mean. And is there really a mean or average response that is representative of everyone? That is often very difficult because of diversity. Between participants' samples or designs are okay for Sir Ronald Fisher, who studied crop yields in agronomy, but humans are not beans. So within subjects' design, where you repeatedly analyze individual responses, may be more appropriate in biomechanics, where those individual responses and experimental mortality are pretty serious issues, rather than losing 3% of your beans but still having a better aggregate crop yield. So a more subtle design I'd like us to think about and talk about too relates to the actual goal of your study and planning your study out. Where do you seek the evidence to contribute to the hierarchy of the research or level of evidence of the knowledge of the field of biomechanics? Kind of at the first level, of course, is an exploratory study, where you study a phenomenon to generate hypotheses after the fact that can be followed up. This is usually done with maybe a more lenient type 1 error rate, and that is explicitly different from a confirmatory research design that carefully collects data based on an a priori hypothesis, where preliminary evidence is now being followed up and we're trying to make a strong inference that we can apply to build a theory or apply the knowledge in a larger context, generalizing it to the larger whole world that we need this at. And this might be a case where you might allow a different alpha level than a more lenient one, but still the trends are recently, because of the numerous tests of correlated dependent variables, that more and more fields are talking about even stricter type 1 error rates when we're trying to make strong inferences to the real world. And remember, finally, these design issues of planning your study go hand in hand with the statistical models in the analysis and how you interpret your data. And the recent reforms to try to do better quality statistical analyses that match our research design are very, very important. Otherwise, we often make mistakes. And the mistakes in biomechanics are common. Biomechanics research is flooded by studies making univariate statistical tests of numerous associated and time-related dependent variables, oftentimes from small samples. And this inflates the experiment-wise type 1 error rate and results in numerous false effects, with little knowledge of which of the effects are real and which are those false positives. And the numerous univariate statistical test of dependent variables is just one of many questionable research practices. A recent study in my field of sport and exercise medicine reported study hypotheses being supported in plausibly high rates. And this is presumably because of the small samples and the questionable research practices that favor finding significant results, and of course the journals that are biased toward publishing results with some sort of statistically significant effect. Now let's talk about sampling, which might be most relevant to the panel discussion we'll be talking about on diversity, and the dominance of samples of convenience in our field, and the biased nature of these samples to the diversity of humans and their actual movement. And we won't see that diversity without actually larger samples that are randomized. And this is perhaps most commonly popularized by Harvard evolutionary biologist Joseph Henrich and his colleagues, who popularized this problem of sampling in psychology research. And they talked about more than the traditional, most of the psych research is done on psych undergraduates that are only 5% of all college majors and are certainly a very much smaller percentage of all the people in the world that have different ages, sex, ethnicities, interests in psychology. And he summarized it in this interesting acronym called WEIRD. Is psychological research weird? Because most of the participants in the studies are Western, educated, from industrialized countries, rich because they are going to college, and from democratic societies. And so this is a picture of his new book that's coming out that explores this a little bit more than just in the psychology area. But we should think about this too in biomechanics. Is our samples that we study representative of the populations we're really trying to get at? Or are they biased in some sort of way? Are they weird? So I've looked up some examples of this for us to discuss, and it's all too common in science. This is a good study in PLOS Medicine that talks about even after federal regulations required biomedical research to mandate greater diversity in the participants in research, we still had the underrepresentation of various ethnicities and underrepresented populations in actually federally funded biomedical research. And in kinesiology, I found this interesting study that talked about 4 particular issues of cultural differences in movement that are completely ignored from the Western perspective of most biomechanics research. I mean, what resting posture should we study? Standing or sitting? There are many cultures where people squat and hunker and squat down or hunker to rest rather than sit or stand. There are different dance styles from different cultures, different cultural ways that people carry loads on their shoulders or around their back, and then even skills that are common across all cultures, like making and throwing pots, have different hand movements and techniques from different cultural experiences in different parts of the world. And then the list of this idea of not diverse sampling in biomechanics is widespread, because our research is routinely biased and underrepresented because we commonly use young, able-bodied, Western white students that are available to us for our convenience samples. And then we analyze them oftentimes with aged or elderly data, cadaver data, and much less often with culturally specific data. The Yoki's data is specific anthropometric data for Japanese children, and we have a limitation of population-specific anthropometric data, despite a huge field of kin anthropometry and a lot of research on different body shapes and dimensional differences in various sports and cultures. Most interesting maybe to biomechanics is knee prostheses here that actually are biased against that deep squatting behavior I was talking about, that actually designing the prosthesis in such a way that it actually might be suboptimal for various ethnic populations. This particular study on significantly different muscle fiber and tendon lengths in farmer and hunter cultural tribes in Uganda. Other ones that are interesting to me, and from kinesiology and exercise science, we see a lot of studies on this, and yet we also too in our field specifically tend to oftentimes ignore these at our convenience. For example, the differences across the sexes not only just affect body mass and lean body mass, but stature and strength. And when we normalize these things correctly, a lot of times the differences between males and females shrinks to probably insignificant levels. Is the person skilled? And what type of skill they're in? There are several research studies in the biomechanics of jumping and the styles of the vertical jump that are taught in dance, the arts, versus the type of vertical and jumps that happen in sport that are taught by coaches. In kinesiology, exercise science, there are unfortunately not really good consistent definitions of the level of skill, or whatever type of skill you're trying to get. And this is the sort of 5 levels that I would advocate for that would be consistently used in biomechanics research. As you have novices that maybe just are habituated and try a skill. Beginners are working on it. Intermediate and advanced are the 3 classic levels in the motor behavior literature. But really, a person can be very advanced golfer or tennis player or whatever clinical skill or movement skill you want. You don't become elite until you qualify for international level competition like world championships, the Olympics, or maybe the highest level of professional sport. So knowing the skill level will naturally generate different movement behaviors. Other movement behaviors are across basically injury status. And of course, definitions of injury are very controversial in the sports medicine field. But you can see that there are actually easily 4 categories that need to maybe be represented if you're wanting to know about the biomechanical issues related to technique across the injury status or a certain kind of injury, because there literally can be at least 4 levels of. And the last one, of course, is movement development over the lifespan, that your movement changes from a child to adulthood to elderly and to very older adults, and all those things all need to be represented in our research sometimes because it affects our research question. So human biomechanics research also comes with sampling method complications, and it turns out that participant learning and accommodation to the actual movement task and the instruments we use might affect them. And in the psychology world, if you've had a psychology class that discussed Hawthorne effects, the classic Hawthorne industrial engineering experiments, how just doing the experiment itself created kind of a placebo or a psychological or effect on the participants. To my knowledge, in biomechanics hasn't been studied extensively. I've seen 2 kind of interesting studies, and let me just talk about them, to how our sampling might be biased because our participants might not be moving as they normally would because they're interacting with the dynamometer force platform, or even, for these 2 examples, video measurement or high-speed film measurement, because that is the least invasive biomechanical analysis system, but still we have evidence that it actually does happen. And I'll start with Jackie Hudson. If you don't know about Jackie Hudson, I encourage you to look up some of her work, a lot of work on basketball shooting, on female performance that's mass and stature normalized, which is very interesting. She did an early study on free throw technique, and she had skilled collegiate basketball players, and then they also had another group that was the unskilled group, which were college students in a basketball class. And they were tested in 2 conditions: a control condition where they shot these free throws. Notice this is just shooting percentage, so this is how well they made the free throws. And of course, the unskilled people didn't make nearly as many as the college basketball players. But the interesting here is the statistical interaction between the skill level and these 2 conditions. She actually had 3 conditions in another study that was very interesting. The control condition is just recording the shots. The experimental condition is the camera is there and they're doing video measurements, and this is after they put some reflective markers on them, of course. And you can see that the skilled players did better when there's psychological pressure from being an experiment and the camera rolling, and the unskilled participants did worse. So that was the interaction. And she was the one that was trying to publish this work in the top journal in biomechanics, and the reviewers rejected it, not for good, sound, logical reasons, but I think out of fear of talking about a Hawthorne effect in our field. This was eventually published in an Olympic Scientific Proceedings conference book, but Dr. Hudson was told that her research was unacceptable because it was using video measurements of kinematics, not high-speed cinematographic measurements at the time. That, of course, has a little bit more resolution and better accuracy, but there's nothing wrong with these data other than that it pointed out that our experimental technique might affect the results, and that was bad news. So naturally it's been empty fallow ground, and our field has rarely looked at it. Robles Garcia looked at it in gait analysis with 2 different populations, Parkinson's patients and then young and elderly controls, and basically found the similar results to Dr. Hudson, that there were small to moderate size effects of the actual experiment, and the same thing in Hertz. So think about it. There's limited evidence we have for the invasiveness of our actual experimental techniques themselves, and just doing our study might actually influence some of the kinematic measurements of our participants. And remember, that is the least invasive of the techniques, because dynamometers are strapped into horse platforms you might be targeting. treadmills and lights and probes and things like that, and reflective markers all affect people. So much human research, particularly in biomechanics, suffers from small sample size. Now, this is a historical problem, mostly because of the costly data collection technology, the time it takes for modeling and computation. And if you look at the mean and the median sample size in biomechanics from my previous studies, you find that these are particularly small sample sizes. And if you use a typical a priori or a after-the-fact power analysis to find out what sort of sample size you should have had, or a priori if you did it ahead of time, the G-power analysis would say you'd have to have 50 participants in an analysis of variance with 3 groups. So my question for us to think about in our discussion is, how can anyone in our field take seriously a study that has 8 co-authors, only 16 participants in the study, and their study analyzed 32 dependent variables from those 16 participants. So they run 32 statistical tests on 32 biomechanical variables with really only 16 participants. And you can see from this just one example that the typical sample size in biomechanics aren't very good to be able to detect anything of meaning. So this small sampling results in very low statistical power in our field, and that will give us inconsistent results over many studies from many false positives and inflated effect sizes that are from these false positive results we report. And this was obvious from my review of this problem in biomechanics. One of the things I looked at as an example were the effect sizes of the 10 most recent biomechanics meta-analyses. Now, in this study here where I reported this, again, you think about this. These are the huge meta-analyses of reviews of some of the best funded research in biomechanics, so that we could have multiple studies and enough evidence to meta-analyze 130 effect sizes. But less than 10% of those effect sizes were small. And if you look at this distribution of the effect sizes of those 130 effect sizes in those 10 meta-analyses, you can see that they're very biased toward very large effect sizes, and small effect sizes are extremely rare. So results from studies of small convenience samples in biomechanics were primarily relevant to only the samples that those data were collected from. They were not even relevant for inferences to the apparently weird populations or samples that they were hoped to generalize to. And the last quality issue that I'll present with you today, I refer to modeling and statistics. And these refer both to the analytical theoretical models we use in our research and the data and statistics models that we have to run on our research designs. And of course, we're very cognizant. Our biomechanics history has a lot of research and debate on the biofidelity of our model. Anybody is a really nice trademark, but the reality is the mean or median data probably isn't that relevant for many of our participants. Not everyone is exactly the same. It's a great trademark, but it's way too optimistic a term. And there are dangers in overfitting our data of our signals. Then naturally there's risks of errors in overfitting a model. But let's just briefly, because I'm not an expert on this, there is a tension in our field between the realism or biofidelity of our models and their parsimony or interpretability. That we can make a very elaborate model, but that makes it very hard for us to interpret changes in various factors within it. So again, this is not my research, and I'm not an expert on this, but we do need greater clarity, in my opinion, in reporting and citing of the validity and reliability of our models and our methods, and the particular purposes that we're trying to use with them. We have many black box data collection and analysis and computation systems now, and we often don't know the biofidelity and accuracy of our models for a diverse anatomy and populations. So I'm just using some slide David Lloyd did at the previous International Society of Biomechanics and Sports Conference. This is some cutting-edge work based on his Dyson Award lecture, and he and his colleagues have shown improved accuracy of joint contact forces by going from just the generic sort of biomechanical model to a subject-specific model where high quality imaging is used to customize the model, and the joint contact forces predicted by inverse dynamics combined with this open simulation is dramatically improved when we have very specific, person-specific data rather than just generic plug-and-play human averages. What I am more familiar with is the error in statistical analysis and the models we use when analyzing biomechanical data. Again, remember, 3/4 of the biomechanics studies report numerous univariate statistical tests of dependent variables. And you add that to the very small sample size, and we're flooded with very poor quality exploratory studies that are incorrectly interpreted as confirmatory evidence of really important biomechanical issues. Again, so let's go up here and look at the traditional sort of thing from our data, the typical study versus an ideal confirmatory study. In biomechanics, we might test a whole bunch of dependent variables with a very small sample size of 20 participants. Ideally, if you follow statistical analysis and good design practice, you would only have a couple indicator dependent variables, and you would have a very large number of participants from a well-defined population. And then even if you had to do two statistical tests, 3 or 4, then you would have a very easy way to progressively correct for alpha inflation by doing 4 statistical tests on 4 variables when you're really only supposed to do 1 or 2. So you can see there's a very wide gap between what typically is done with our statistical models and what we really should do. And most recently, perhaps our most numerous statistical tests of correlated biomechanics dependent variables are also biased because not only is there this inflation of alpha from the multiple statistical tests, is that our data are time related. And Todd Pataki and colleagues have been leaders in talking about specialized statistical tests to do functional data analysis for statistical parametric mapping. So if we have a curve of data, we can do a statistical test throughout it and take advantage of knowledge of the time series data and the relationship of variables that are next to each other in time. So there's lots of ways that we need to work to improve our statistical design to get robust answers that are biomechanically true and meaningful. And you can read more on these common errors in traditional statistical analyses in biomechanics in my 2009 article. But since that time, Todd and many others have done a lot of great work to give better guidance on the most appropriate statistical analysis, how to avoid questionable research practices. And the recent last couple years, the American Statistical Association's position papers on avoiding these traditional errors on null hypothesis testing has driven a lot of journal position papers. This one right here, all the associate editors of the Journal of Sports Biomechanics just recently, a couple months ago, published the recommendations for statistical analyses in that journal. British Journal of Sports Medicine just within a month or so, week or two ago, published this commentary on statistical consultant needs for more statistical consultancy. So statistical analyses are done correctly and reported correctly, and people can follow along. And down here is just an example of a recent recommendation for plotting change scores in experimental studies to accurately report the individual and the group responses, which kind of brings us back to where we started with Barry Bates, within and betweens. Even if you do a between subjects analysis, reporting a mean and a standard deviation is the bare minimum. That's good. But a violin plot, Tukey Block's plot, or various these other change plots are much more useful to explain the average and the extent of variation of individual responses. This little picture is good, but these other ones tell you a whole lot more information about the individual response to this particular intervention. So there's lots of opportunities for improvement. So biomechanics, again, has much to contribute to the theory of human movement and application in a variety of areas. We can make improvements without too much cost if we hold high standards for ourselves and each other in our research design, analysis, and reporting. I suspect the biomechanists in the future who win the Fung, Wu, Hay, or Murray-Bridge Awards will not be the scholars who are hot, or they will be the scholars who don't ignore diversity and don't repeat their mistakes of the past and do the highest quality research. Seeking the best quality research questions, models, design, and statistics, and clarity of reporting is something we should all aspire to, and we can talk about in the live panel discussion. Thank you for observing and listening to my presentation.